Good morning. It's a beautiful Friday morning. So I'm going to try to explain something new today. Let's go back to what we did already. You looked at a normal distribution like this. This one has a mean of 66.2 and a standard deviation of 14.1. If you have this distribution, you can now calculate probabilities that it's between certain values, under certain values, above certain values, with PDF normal or normal PDF, sorry, CDF. You can also calculate, hey, if the probability that it's more than 70, say, so if you get a probability, you can calculate what the boundaries are within the norm. Very powerful tools. Normally we look at 2 times the standard deviation. Within 2 times the standard deviation, we say, hey, that is normal, we don't have to look deeper. Outside the 2 times standard deviation, maybe there is something going on. For today, we're going to look at, here, for instance, I have the weight of apples. These apples are taken from trees in the shadow. I also weighted or took the mass of trees that gave apples, and those apples were in the sun. And I got a normal distribution like this, the red one. So I'm now wondering, looking at my 2 graphs, the trees in the shadow, did they give apples that have lesser weight, or of the apples in the sun, or not? Or are they actually the same? So what should I conclude? So what I'm going to try to do here, I'm going to try to compare the 2 means. So this one here, that was 67.5, and this one here, 66.2. So can I use a test that tells me, nah, they are different, yes. Or they might be different, or they are actually the same, statistically. Now you can use this in many different ways, or in many different questions. So let me go to my next step. And try to explain a bit. And what I was saying, I'm looking for a test that can compare 2 means. So are the means different, or are they the same? That can be because of anything. We call that the t-test. First of all, both distributions, they must be normal. If you don't have a normal distribution, you can't use the t-test. Remember that. As I said before, in social sciences, they often do it, but they shouldn't. Because the whole t-test calculation is done assuming normal distribution. Let me give a few examples. As I said, the weight of apples in the sun or in the shade. The number of days to recover from a flu with medicines or without medicines. Important at the moment. The height of women compared to the height of men. Or the heartbeat before you do exercises or after you do exercises. So in each of these 4 cases, you look at 2 different means because of certain reasons. In number 2, we have without medicines as the control, and we are comparing that with medicines shortening the flu. In number 4, we have as the control the heartbeat before exercises, and then we compare that with after. We assume that it will go up. So the mean of after the exercise will be higher than the mean before the exercises. I don't know what the control will be in 1 or in 3. Because we are comparing two different things. You could say, okay, I want to compare in the sun with the shade or in the shade with the sun. I think that was the first one. Let's move on. So we have here some examples. I'm sure you can imagine many of them. But you obviously must have two sets of data. You can be interested in different things. First one being, is the mean of one of them less than the mean of the other one? And that is, for instance, in number 2. You want the mean of to recover from a flu to be less with medicines than without. Otherwise, there's no use of taking medicines. We call this a one-tailed test. Is the mean higher than the mean we are comparing with? So this is for number 4. I would think that the mean after exercise, and I'm expecting that it will be higher than the mean before the exercises. Again, this is a one-tailed t-test. You're only looking at one side. Or you could look at, is the mean different, or are they different? So one can be higher, the other can be higher. I don't care actually that much. That is called a two-tailed t-test. That could be number 3, although that is usually not the case. Or it could be my example, number 1, and maybe they do better in the shade than in the sun. Could be, I don't know. So for number 1 and 3, I would do a two-tailed test. For number 2, I would be looking at, hey, the first example, the mean of with medicines is less than without. And for number 4, I would look at the mean after exercise is more than the mean before. I hope you're still with me. Next part. Before we do the test, the t-test, we will first have an hypothesis. So we will assume that they are the same, the means. So that is our null hypothesis, always and ever. So the null hypothesis will say, again back to the apples, the mean of the apples in the shade is the same as the mean of the apples in the sun. And I'm going to see if I can reject this statement, because then they are different, or if I have to say, no, that seems to be true. So this is the null hypothesis. The two means are the same. We have an alternative hypothesis, and that is the mean of the apples in the shade is less than the mean of the apples in the sun. So here I actually assume that sun helps. So null hypothesis, they are the same. Alternative hypothesis, they are different. I don't know why there is here a T. So let me take that away. Don't like it. Gone. Next step. We can test at different confidence levels. It depends a bit how precise you want your conclusion to be. In statistics, we normally use 3 different confidence levels, 10%, 5%, and and 1%. If you talk about 10% confidence level, we say, hey, what we want to look at is that only for 10% of my data, the means, I'm looking at the word just, anyway, doesn't matter. So that the means are different. So if I get from my t-test p is 0.1 or less than 0.1 and 0.05, 0.02, then I will say, okay, the probability that it is by chance that they are different is less than my confidence level. So I will reject my null hypothesis. I will say they are not equal. I can do the same with 5%. The t-test will give you a probability. If the probability is less than 5% or 0.05, say 0.01, then you will conclude under the 5% confidence level, I reject the null hypothesis. They do not seem to be the same. And if you want to be even more precise, you will use a 1% confidence level. So if the probability is less than 1%, that it is just because whatever, not because of what you're trying to test, then you say, hey, it's below the 0.01, I reject the null hypothesis. If it is above the 0.01, I accept the null hypothesis. Then I will conclude the means are the same. Being in the shade, being in the sun, it doesn't matter. Being a woman with your height, being a man in your height, it doesn't matter. There are no influences there, it seems. Lastly, we usually choose 5%. As I said, the t-test gives you a p-value. It also gives you a t-value. We don't use that t-value in our course, so we always look at the p-value. As I say, for the 5%, if it is less than 5%, the p-value you get from the t-test, we reject the null hypothesis. If it's more, we accept. So if it's more than 5%, the means are the same in our conclusion, or at least we cannot say they are different. But if it is less than 5%, under the 5% confidence level, we can say the means are different. So maybe that is because the sun and the shade. Maybe it's because you did exercises and the heartbeat went up. You don't know that, but you know we statistically can say they are different. That's that part. Okay, let's see what you need to do with the calculator. As I said, you have two sets of data. Put those data in, and you've measured different things, and go to Start, Edit. So where am I? Start, Edit. I have already put them in. I put here the data that I measured for, say, in the sun, the shade, the weight in the sun, and I have put in L2 the weight in the shadow or in the shade. So you need measured numbers that you put in L1 and L2. You can see they don't have to be the same length. After you've put those in, those L1 and L2, as I said, these two can be my examples. Go to distribution. No, not true. Go to Stat. And we go to Test. We have here two sets of data. So we're going to tool sample t-test. So don't use the t-test itself. Go to the two sample t-test because we always will compare two sets of data. So go to number 4, enter. Here you see the data. My data are in L1, so let me put L1 and L2. If you would have frequency lists, you can put them here. We don't. And you see here now the two different types of tests. If you say, hey, the mean 1 is unequal, not equal to U2, that is the two-tailed test. If you say, hey, the mean 1 is less than the mean 2, that's what I want to find out. It's a one-tailed, or the mean is more than U2, or the mean 2. That is also again a one-tailed test. One-tailed, one-tailed, two-tailed. Don't worry about pooled, always put yes, and let's calculate. I have now done the two-tailed test. Calculate. I get here a p-value of 0.82. 816. Obviously, that is way, way, way higher than 0.05. So my conclusion is there is no difference. Had the p-value been 0.01, say, then it would be way, and then I could say I can reject the null hypothesis. So again, let me repeat. Put your data under stat edit. So put them here, the two sets. Those are the two sets you're comparing. Both of them have to be a normal distribution, or at least very close to a normal distribution. And then test it on the, start test on the two sample t-tests. We compare two sets of data. We are not looking at the t-test, so number 2 itself, we are looking at comparing. Put your L1 and L2 here, list 1, list 2. You can do a two-tailed test. Let's now do a one-tailed test. Is the first mean less than the second mean? Don't worry about pooled, just put yes and calculate. Now I get a probability of 0.41 or 408. Still way above the 0.05 I'm looking at. So again, I am accepting the null hypothesis that they are the same. You see one more thing here. You see here df, that is degrees of freedom. I will talk about that when we do another type of test. I hope I have been clear. Try to do the exercises that I put and see if you get it. If not, automatically look at it again or email me and I can answer. After this and after this afternoon, have a good week. And we will be on holidays. I know you cannot do much, but at least you can take your mind a bit away from all the academic learning, all the screen time, all the time you have been looking at your computer. Stay well.